Okay, so then I will. Okay, this is the program that I just shared with you. Tomorrow morning, 9 o'clock is the inauguration, and 9:20 is the first technical session. So it's going to be interesting, even though we are not able to meet the speakers physically, but it's a very nice group of speakers. So I think you will benefit a lot. All right. So back to our course, back to chapter 5, back to the numerical approximation for a PIDE. So last day we started out with the Levy process driven jump activity stock price with a particular density function. We also derived the PIDE that we really need to solve, which is equation 5.5. And before getting into actual approximation, we have done some change of variable and a little bit of manipulations. So that now our target equation rather than 5.5 is 5.19. So 5.19 is our target equation. There are certain new functions here like omega and sigma square, but these are completely known. So we can also find good numerical values for them. So that's where we stopped Wednesday. All right. So now let us start discussing the actual discretization process as we have been doing for chapter 4 also for the usual PDE problem. It will be similar here. The only additional element is this particular integral. This integral will have to be approximated properly. The rest of the terms, we will be using same strategy as in chapter 4 for the PDE solution. The integral, we will discuss how we should be getting a good approximation for this one. So in whatever we discuss, what we are going to do is, we know that there is a singularity for y at 0, so that point has to be treated with care. So what we will do is, we will treat the integrand near the singularity somewhat implicitly. So we'll somehow skirt around the 0 point. You know what skirting around means. We'll skirt around the 0 point and treat it implicitly, but all the other terms will be completely explicitly treated. So it's a fully explicit treatment for the rest of the grid, but only that part y equal to 0 we have to be careful about. Okay, so the grid definition. So again, we are talking about an option, and in particular, let's talk about a put option, because as I said, if we understand the uh, algorithm for a simple put or a call, once we are clear about that, then we can of course go forward and talk about more complicated options. So let's talk about a typical European put option. That will be our standing example, but the process remains true even if the contracts are more complicated. So for an option with maturity capital T, we consider M equal subintervals in the tau direction, in the time direction. So this is the standard thing that we do. For the X direction, which is log stock price, N subintervals between X minimum and X maximum. So now there is now a choice of X minimum and X maximum that will be involved. But we have been doing that before also. So we have this mesh or this grid, rectangular grid here on capital D, which starts at X minimum to X maximum cross 0 to capital T. The steps are of size delta X and delta tau. So there are n plus 1 steps in the log stock price direction and n plus 1 steps in the time direction. So that's our grid. And a sample grid point, the notation will be xi tau j. it will be xi tau j, and wij be the approximation of w, the function w at xi tau j, because this is the function that we have to understand. This is our actual function with a change of notation. Remember, just the w is nothing but v, our target price. Okay. So wij is wxi tau j. We will start by forming difference equations at a particular grid point xi and tau j plus 1. As usual, the assumption is the discrete values wij at time tau j are known. So it is like I have solved up to time tau j, and we are solving for time tau j plus 1. So we are going forward. So knowing wij, I am going to solve for wij plus 1. Okay. So for the del w del tau term, we are going to use a first order finite difference approximation. For the del 2w del x square term, we are going to use a second order approximation. And for del w del x, we are going to use a central difference approximation. So again, this is familiar, so we don't need to detail it further. That's the standard strategy we have been using. So first order for time derivative, second order for second derivative, and central difference for del w del x. And of course, we have to choose an epsilon, and the natural choice for epsilon would be delta x, the grid size. So that's the minimum step that we are allowed on the grid. So epsilon will be equal to delta x. So basically our neighborhood around 0, is minus delta x to plus delta x. So with all that, we will obtain this discrete equation, in place of our PIDE. So this 519 is now written in the discrete form as here. So this is by del w del tau. This is the central difference of del w del x. I have this RQ, the W function is still here. We have to omega delta x. This omega will come from here. And finally, the integral remains as it is, accepting the fact that the range is now specified with epsilon equal to delta x. Okay, is it clear so far?
Yes, sir.
So I am using the first order, the central difference, and the second order for the derivatives. Similar to what we did for the PDE problem, the integral we have to handle now with the proviso that epsilon is chosen to be delta x. And this we write as approximately equal to 0, but of course we are going to set it equal to 0 and solve. This approximate because we know that this algorithm that is being developed is only correct up to a first order in delta t, because we have taken a first order approximation. So it is really approximately equal, but you know. So this equation, this equation here is equivalently written as this equation. So I'm just rewriting it. The integral is taken to the other side along with the wij point. Okay, so everything else is the same, only the integral and the wij point is taken to the other side. That's the only change that we have done, because this part we are going to tackle separately. And we multiply throughout by delta tau. Okay, so now again we have to introduce some shorthand notation, because writing this out every time is cumbersome. So let us define BL as this whole thing, the scaling of the approximations with sigma square minus this whole adjustment. So this whole scaling adjustments appears here. This is the big term here that appears as the scaling adjustment as a coefficient of wi minus 1 j plus 1 that I call BL, and also define BU as this coefficient, where BL and BU are very similar except the minus sign here is replaced by the plus sign here. So this is BL and this is BU, and they appear here and here in the redefined difference equation. They appear as coefficients for wi minus j plus 1 and wi plus 1 j plus 1. So these two I call BL, BU. With that, the equation looks simpler now. It is like this: minus BL times this plus whatever was in the middle, then BU times the wi plus 1 j plus 1 term equal to the original thing as before. The integral is the one that we have to handle. So this is our shorthand for the difference equation, or this is our shorthand for the PID. We are considering a a put option. So Wi0 is defined as k minus e to the power xi plus e to the power xi, because we are working on the log stock price. So actually s is e to the power x, and time 0 means actually maturity, because tau is capital T minus t. Okay. So
Yes, sir.
This is our new equation for the PID, and this is like the initial condition. And of course, we will add some boundary conditions later. Okay, so this is our task now. So we have to solve this particular equation along with the initial condition, and we already discussed last time on Wednesday that we will be using the Neumann boundary conditions on the derivatives, the partial derivatives directly. So we'll get back to that, but first we have to take care of the integral. So evaluation of the integral term is our next task. So what do? I have this mod y greater than epsilon or mod y greater than delta x integral with me. So we subdivide it into 4 parts. Why 4 parts? So that's the thing. Okay, the 2 middle parts are quite intuitive. The 2 middle parts are basically the negative side and the positive side inside my grid. So this x0 minus xi up to minus delta x is the left hand side of the grid, left half, and this plus delta x to xn minus xi is the right hand half of the grid. Of course, I have to start and stop one point before, because I must take care of this wx plus y function remaining inside the grid. So if y is xn minus xi, then the argument here will be exactly xn. So I have to make an adjustment here and here with xi. Okay, is that clear?
Yes, sir.
The other 2 terms are the extreme parts. The first term here is minus infinity up to the left of the grid. And the last term here is right of the grid up to plus infinity. So these are the extreme terms, which we will handle separately, simply because this is not part of our usual grid. So we will be using the boundary conditions here. When we are evaluating these integrals, we will be using boundary conditions. We will see. So there are 4 terms, and we will discuss how to evaluate them one by one. Okay, so this is just to summarize what we were discussing just now. The rationale for cutting it into 4 pieces is that in this region, y greater than mod y greater than delta x, we have 2 subregions. Of course, one is the negative side and the other is the positive side. That part is intuitive. For the negative side, I want xi plus y to be inside the grid. So we should have y greater than x minimum minus xi, which is same as y greater than x naught minus xi, which will be minus I delta x. So if I am at xi, then I have to make an adjustment. I must make sure that y must be greater than I minus I delta x, which is x naught minus xi. For y less than x naught minus xi, the quantity will be outside the grid, so I have to cut it there. On the other side, for y greater than delta x, same rule applies. I want xi plus y to be inside the grid, so I must have y less than x maximum minus xi, which is xn minus xi or n minus I delta x. So these are the two lower bound and upper bound respectively of the second and the third term, as we explained earlier. So that's why we cut the lower bound and upper bound there. For this second integral, x naught minus xi up to minus delta x. So this is the one we handle first, x naught minus xi to minus delta x. What we do is, we look at this integral and we insert the actual density function. We have the form of the density function, and this is the negative side. So I know exactly what the density function will be. This will be minus lambda n mod y. Okay, remember the density had two parts. The density we are working with, let me go back up. The density had two parts, and for now it is this second part that is relevant because I am in the less than 0 zone. Okay. So I insert the density, and then I write this integral as summation over each of the grid pieces, over each of the grid horizontal slices. So from k equal to 1 to I minus 1, remember that that is my range, I minus 1, k delta x to k plus 1 delta x. So it starts from x naught minus xi and finishes at minus delta x. And I rewrite it as negative so that I can write a positive sign here. So when k equal to 1, I have this delta x to 2 delta x, which will be translated to minus delta x and minus 2 delta x. So I scroll the interval from right to left by a change of sign. Okay. It is just a trick to make this look nicer, that's all. I'm not changing the definition or anything. And I do this, use the same feature here, so that my mod y has now become only y, because I am essentially redesigning the variable. And because I have also written the summation in this order, the change of sign in the dy is also taken care of, because dy would also be changed to minus dy. So are you okay with this? Can you see what we have done? We have simply written the integral over successive slices of the grid, successive horizontal slices. We have changed the sign so that the summation and the integral limits look nice. As a result, my y variable is changed to minus 1. Is it okay?
Yes, sir.
So this is
Yes, sir.
nothing sophisticated. This is just high school calculus, but we are using it to make the thing look more compact. Now we use linear interpolation, simple linear interpolation on each of the pieces. So interval y belonging to k delta x to k plus 1 delta x, what we do is we write this function wx minus xi minus y tau j as approximately wi minus k comma j, and then this difference this is the rate, this is the slope times y minus k delta x. So we approximate the curve, whatever the curve may be, by a straight line, so that the function w can be written as simple combination of the grid points. So remember, these are the grid points. I already know these values exactly. And the function could have gone through anywhere, but we are ignoring the curvature of the function. So through a linear interpolation, what we are doing is we are writing the function as an approximation using only known grid point values. It is a very straightforward, simple approximation, but if my slices, horizontal slices are small enough, then this would be reasonably good. So therefore, I get the simplified expression here. So my integral, the original integral as in here, now becomes summation integral over each horizontal slice of this function. This is now my approximation for w function minus wij as before times the density. This is what we have. And now just notice that this whole thing here, only this y is dependent on the integrand. So I'm sorry, I'm putting it very badly. This is the only variable part. Everything else is fixed. So I take all the other terms out. Whatever other terms are here, I take them out. Only the integral will be on the density, and this y is adjusted. Oh, what is happening? Something, yes. Yeah, exactly. And this y is adjusted in the denominator here in this term. So what is happening here is that for all the other terms, first this k delta x times this difference and wij, the whole thing goes outside. So integral is only on the density. That is the straightforward part. The only part where y was involved, that part is taken as a second term, and that y is adjusted with the denominator. So the denominator loses one exponent. So it was 1 plus y, now it has become capital Y. So I have two integrals involving the density or very similar to the density, and everything else goes outside the integral. Now to evaluate these integrals, these two here, we have to do some more work. So we do some change of variable. So what we do is, the original integral is now written as this term plus this term. And here I am using a change of variable. So this lambda n y is now written as z. So I have some lambda n power y going outside because of the dz. Here also. So finally, my integral looks like this summation. This summation, the rest of the things are decided before, times this function we call a g2. We call this g2. So, okay, so let me show you this first. So g2 and g1 are defined like this. So g1 xi is a function from xi to infinity integral e to the power minus z, z to the alpha dz, and g2 xi is xi to infinity, the same type of function with the exponent plus 1, because I have two such things. So this is my g2 in the first term, and this is my g1 in the second term. So the integral is called g2. So I can just evaluate it at the upper limit minus the lower limit. So that takes care of it. And The second term is the same thing for G1. So again, for these two new definitions, G1 and G2 integrals, we use them here and write the whole integral, original integral, as two summations, and those summations will also involve the evaluation of this G2 function and the G1 function at the upper bound and the lower bound. Can you all check this and confirm that this is clear? So the first step was just taking out the known terms outside. So the integral only involves the density and something similar to it. The second part was defining two new integral functions, G1 and G2, and then using them. So this is not bypassing the actual evaluation part. The actual evaluation part will be in G1 and G2. So this we will use as two function calls for an algorithm. These would be like two function calls, and those functions will be called in these four places. So is this clear or not?
Yes, sir. This is so.
I'm using these two new definitions, remember, xi to infinity. So when I am doing it on a finite interval, it is basically the difference of two integrals. Same for G1. So two tricks. The first trick was a linear interpolation to get rid of the W function here so that I can take many of the things outside the integration. The second trick was just rewriting the integral part with a compact notation, which can be used as a function call later on. So that I have this particular integral. This is the second integral. Remember, I had four pieces. This is the second piece. The second piece, the complete evaluation formulation is here. Okay. So now for the third piece. The third piece, we will do similar things. So this is for delta x to xn minus xi. We write this integral again as summation over these pieces, difference of the W function times the density as before. And again, we use linear approximation like this. So xi plus y tau j is approximated by this straight line function. And therefore, we will obtain again the integral equal to this summation over integrals. And notice that I can take things outside. I have this again G2 and G1 type things inside, and they can be evaluated. So the third integral is evaluated in exactly the same way. So this was the second integral. The third integral is also evaluated in exactly the same way using the same G1 and G2 functions written like this. So these will be our two parts inside the grid, the left half and the right half. These two parts were the most important because they are inside the grid, and the grid, as you remember, is the relevant part of the stock price range or the log stock price range. Outside that, we are essentially going to invoke boundary conditions. So the second and third term is done. Now for this region, extreme left, minus infinity to the left of the grid. So again, I insert the density function, redefine in terms of minus y. So my integral now is I delta x to infinity, this function difference times the density. Now that we are on the extreme left, which is good for a put option, so we will invoke this boundary condition there. So we assume that the W function is nothing but the value of the put contract, k minus e to the power xi minus y. So in this interval, my W function is just the boundary value, the value of the derivative contract. So I can put it here in the integral. Once I put it here in the integral, many things are known except this e to the power minus y term. So again, I have the first term where I take k and k minus wij outside, and the second term where I take e to the power xi as a multiplication term outside, and e to the power minus y will stay inside. So what is happening is that I have again two integral terms which are looking in the G1, G2 form. So finally, the first integral, the left extreme integral, can be written as again. So now this is G2 because I already have infinity here, and this will be again G2 because the powers are not changing. It is still 1 plus y. Only lambda n has become lambda n plus 1. So this is G2 evaluated at I delta x lambda n, and this is G2 evaluated at I delta x lambda n plus 1, because there was this 1 e to the power minus y coming extra from the value of the contract. Okay, is the reasoning all right? I am using the boundary condition argument and then evaluating the integral.
Yes, sir, it is clear.
Thank you. So because this is a little bit of tedious algebra, so it will require a bit of pen and paper work on your side. So we have got rid of, we have analyzed 3 out of 4 terms, and only the last term is left, the extreme right. And again, extreme right should be easier. Okay, so this is the extreme right. So for this region, so this is capital N minus I delta x up to infinity. Now here, the stock price is very high. So the put option is going to be worth less and less. Because remember that the put option works well when the stock price is actually low. The put option becomes worthless when the stock price is very high. So what we will do is, because we are working on finite grid, for all values in this right extreme, we will assume that this W function has value 0. So the put option is assumed to be worthless. So what will happen is, the original integral, which we write like this, the first term Wxi plus y tau j term, that will vanish, contributing nothing. So I will only have the second term minus wij term, and the value of the integral again will be using the G2 function evaluated at capital N minus I delta x times lambda p. This is on the positive side, so it will be lambda p. Same strategy using the boundary condition, but now the boundary condition is on the reverse side, where the put option contract is almost worthless. So 4 terms we have evaluated. So now let us see where we have arrived. So we were actually here. We had this equation involving the BL and BU coefficients. BL, BU coefficients were defined earlier. Sorry, later here. So these BL, BU coefficients we have used. So we had this difference equation form equal to Wij plus delta tau times the integral. And this integral had 4 parts, which we have evaluated one by one. So having done all that, let us recollect. Putting together all the terms, we obtain this difference equation now. So we were at point xi tau j plus 1. So at xi tau j plus 1, what we really have now is the following. So again, we are using a lot of shorthand. So Lij plus 1 is just minus BL now. So you see, what we are trying to do is we are trying to write it in the usual LDU form, because we remember the tridiagonal matrix structure we are going to use, and we are going to consider that as a function call which is already available to us, solving the tridiagonal matrix system to get the values. So we want to write the new equation system using the old notation. So I change again. So minus BL is now Lij plus 1, minus BU is now Uij plus 1. So the first term and the third term are accordingly substituted, L and U. The middle term was the central difference. So that term we have written out here fully. Again, I go back. So this was the big term here in the middle. This big term involving BL, BU, everything. So that big term we write as D, and this is equal to Wij plus delta tau by nu Rij. Now Rij is complicated because Rij will involve the integrals. Rij is actually sum of all these integration terms. All the four integrals that we collected one by one and simplified, those are all collected in Rij. Okay, so is this clear? There is a lot of notation involved. We started out with difference equations, then we defined BL, BU, and then we are again coming back to the LDU notation to make it consistent with our earlier subroutine. But the crux of the matter is that the difference equation part is written as this LDU notation again, and the integral part is collected in this Rij term, which would be sum of all the relevant terms. So this is just to recall, BL, BU are again written here. So this is what we have in the final form. So can you just tell me if this all checks out? Because there is so much notation, it's quite, it's a bit confusing to see it for the first time. I have all these integrals here, this G1, G2 terms coming out, multiple G1, G2 terms actually. So collecting all of them in Rij.
Sir, can I check this later after
Yes,
seeing it from the
yeah,
book?
yes. I think you will need more time to check this thing. So okay. So what we will do is we'll just discuss the remaining part of the algorithm, and then we'll stop, and then you should check this and confirm that this is clear, because this is definitely quite involved. Okay. So prima facie, this is our difference equation now with this Rij, the composite of all the integrals, with the BLBU notation reproduced here again. Now, how do we go about computing? So we assume that at the completion of time step tau j, the values Wij have been computed. So we solve a linear system of equations to find Wij plus 1 for all I. Now notice that these things, these G1, G2 function evaluations are pre-calculated. So G1 at k delta x lambda n, k delta x lambda p, G2 also, and then G2 as lambda n plus 1 and lambda p minus 1 for each of the k, they must be pre-calculated, and you can check that they are pre-calculated and they are stored. Because G1, G2 functions are known functions, so I can evaluate those integrals separately and store them. As soon as I have decided on the grid size and the parameter values here, so lambda n, lambda p has to be fixed, because to define the density, I need to decide on the value of lambda n and lambda p. But once I have done that, these numbers are all known for me. Fine. Knowing that, we will also need to evaluate the two unknown functions sigma square epsilon and omega epsilon. And again, sigma square epsilon and omega epsilon actually can be written in terms of the functions G1, G2. Sigma square epsilon, which is this integral mod y less than or equal to epsilon y square ky dy, is actually this function. This is the negative part, this is the positive part. Okay, so yeah, where am I? Yes, sorry. So the positive and the negative part. So for the first integral, for the negative part, we will do a change of variable and integration by parts, etc. But you see, this form is very similar to our G2 function forms, G1, G2 function forms. This is G1 actually. So this y squared times ky dy can be written as this, where the integral inside is actually G1 at 0 minus G1 at lambda n epsilon, 0 and minus epsilon. So this is for the negative side, and similarly for the positive side, it will also be in terms of G1 evaluated at 0 and lambda p epsilon. So sigma square epsilon would be the sum of these two terms. So this is mod less than or equal to epsilon, so it would be the sum of two terms, and these are the two terms again in terms of G1, and we know that G1 is already pre-calculated. Omega epsilon is 1 minus e to the power y times density dy. Again, we cut it into two parts. The first part, we can use this G2 function again and evaluate, and sorry, it's the other way around. This is the second part. Sorry, this is the second quantity. This is the first one. Okay. Okay. What is it? So the second term, the positive term, can be written as G2 lambda p epsilon and G2 lambda p minus 1 epsilon terms after some change in the exponent, because I have two functions here, the density as it is and also with e to the power y. So one term will be with lambda n with lambda n plus 1, and the other term here, it will come with lambda p minus 1. So I have a lambda p minus 1 coming from the positive side and lambda n plus 1 coming from the negative side. And we are using this relationship. So the omega epsilon integral collecting the terms will be looking like this. Okay, so this has been quite heavy algebra. So let's take a break, 15 minutes break, and when we come back, we will talk about whether these expressions check out, because we need a bit of time, a bit of a breather to absorb this. So did you check the expressions?
Yes, sir. They are matching.
They are matching. Okay, good. So basically it is collecting terms in different places that is creating the complications. So we have 4 integrals and they are contributing to different slices, and then they are collected in both d term as well as the Rij term. But all is good. We have an expression, however complicated, and that expression involves known functions g1 and g2. So they can be computed and pre-stored. So basically what we have got is the following, that we started out with our difference equation formulation for the PIDE, as in here. Then we introduce some shorthand notation to write it in a more compact form. But the main challenge was evaluating this integral. And this integral was cut into 4 pieces, which are all evaluated separately. But the evaluation either involves a boundary condition where the function can be simplified, or inside the grid, they involved a linear interpolation. So the linear interpolation also made the functional form simple. We have used definitions of 2 integral functions, g1 and g2 repeatedly, and then collecting all these integral terms, we have this final difference equation here, which is made to look like our original finite difference tridiagonal matrix system using the LDU notation. So L, D, and U are now involving all the earlier BL and BU coefficients. BL, BU are here, as well as some of the contributions from the integration terms. All the remaining integration terms are collected in this Rij here on the right hand side, which is big because it collects everything from the 4 integrals, everything else. So finally, we have an equation system which look familiar in the sense of our usual tridiagonal system. So that's what we will be able to solve, knowing the function values of this g1 and g2 at all these points, and also checking that both these functions sigma square epsilon and omega epsilon can also be written in terms of our g1, g2 functions. So sigma square epsilon can be written as this combination of g1 functions, and omega epsilon can be written as a combination of g2 functions. So this is omega epsilon here, and this is sigma square epsilon here. So these were all the computational contributions. They will involve G1, G2, or linear approximations. So linear approximations will lead us to a linear system of equation, and it will be tridiagonal again. The only remaining consideration is to understand how the boundary conditions are going to be handled. We discussed before that we are going to use the Neumann boundary conditions, which is directly on the partial derivatives. And in terms of this particular system, the boundary conditions look like this. So the limit x goes to minus infinity del 2 w del x square minus del w del x is taken to be 0 for all tau, for all time points tau. And also when it goes to plus infinity, it is also again taken to be 0 for all time points tau. So this was originally stated in equations 5.9 and 5.10 above. So this was the original boundary conditions that we stated earlier, the same things. Okay, this was 5.9 and 5.10. We are just rewriting it because now the objective is to find a numerical version of these boundary conditions. So these boundary conditions will now need a numerical version. Okay, so we'll discretize, same strategy. We discretize. This is the second derivative and this is the first derivative. So this difference should be equal to 0, or equivalently, we use the half step argument. We have used the half step arguments earlier. We can write it as this equation, this equal to 0. For the boundary points, x0 and xn are our boundary points because that is where we need to understand the boundary conditions. We will apply this 523. We will apply this equation 523 at I equal to 1. I equal to 1 will be at the x0 point. We can solve for w0j plus 1, the value at I equal to 0 as this. So this will be our boundary condition evaluation. And again, if we apply this equation 523 for I equal to capital N minus 1 for the other extreme side, we can solve for w capital N j plus 1. So we use this equation 523 once for I equal to 1 and once for I equal to capital N minus 1 to solve for w0j plus 1 and w capital N j plus 1. So these two will provide us with the boundary values. Now, we have already written the whole difference equation in a reasonably compact form like this: LDU terms plus Wij and something else, this whole big Rij. So this we are now going to work with. So suppose at xj tau k plus 1, so it is jk plus 1 point, the difference equation looks like this LDU system Wij plus the whole of the right hand side. The right hand side was all the Rij terms. And Lij plus 1 are the lower diagonal elements, D are the diagonal elements, and U are the upper diagonal elements, as we had before in our stiffness matrix. Then for j equal to 1, when I put j equal to 1 here, sorry, not j, I equal to 1 for the first time. For I equal to 1, I have this system. Why do I need this? I need this because this first system of equation involves w0j plus 1, and w0j plus 1 we had to evaluate separately from the boundary conditions 524. So w0j plus 1 has to be evaluated like this 524, which is inserted here. So we substitute 524 and we gather terms because this will contribute to both w1j plus 1 and w2j plus 1 like that. So once we collect terms here, it will be an equation involving w1j plus 1 with a changed coefficient and also w2j plus 1 with an adjustment here. So these adjustments are coming from w0j plus 1. So for the first slice, I equal to 1, we have this adjustment. Similarly, when we arrive at the last slice for capital N minus 1, again, we will be using the second part, 525, to substitute for W capital N j plus 1 to get this equation. So again, this would be L plus the adjustment, and here D plus the adjustment for the last slice. So our whole system of equation, which was defined earlier using all the shorthands and integrations, that we will be using in the matrix system, except for the first and the last slice. Sorry, first vertical and the last vertical. There we will have to make adjustments for the Neumann boundary conditions using 524 and 525. Okay. So what are we doing here? We are essentially looking at the system of difference equation. This one, this system here, with Neumann boundary conditions. So for Neumann boundary conditions, we are getting the values of W0j plus 1 and Wnj plus 1 in terms of these terms, which we will insert back. So in the whole system, in the first slice and the last slice, we will have a different coefficient, and everything in between will have the usual LDU coefficients. So it is again a tridiagonal system, but only for the first and the last step, we have to make an adjustment. And this is exactly what we have done before in most of our finite difference tridiagonal system equations used in chapter 3. Okay. So is this clear now? Or
Yes, sir.
Yeah. So basically it's the same system with adjustments at the first and last term, tridiagonal. So again, we are back to that order of n computation routines. But of course, the steps inside are more now because we have to do a lot of computations using the G1, G2 integrals. So finally, collecting everything, what we have done here, let me just go back and quickly recap. What we have done here is we started out with a Levy process driven stock price. We wanted to price the derivative contract V. So that derivative contract price can be written as a combination of usual PDE plus some integral term which takes care of the jumps. So when we set up the usual risk neutral world riskless portfolio argument, once we are able to set up the riskless portfolio argument, use the properties under the risk neutral probability, this property, then we finally arrive at the PIDE 5.5 for the derivative contract. And then we do some change of notation to arrive at the changed PIDE. That was yes, 519. So we do the change of variable and make some adjustments to the integrals to get 519. 519 involves an integration, so that has to be handled separately. In our discretization algorithm, which we have discussed so far today, we have discretized the usual differential part easily. That was not complicated. We know how to do that. The integral part had to be handled separately. So we arrived at a point where we have a system of difference equations looking like our original tridiagonal systems, except on the right-hand side, we had an integral. And this integral is then evaluated in 4 separate steps, depending on what range of the log stock price we are considering. That evaluation involved either linear interpolation or using the boundary conditions. So finally, collecting everything, we have this final difference equation, again in the tridiagonal form on the left-hand side, and this integral collects all the terms here on the right-hand side. That was the final difference equation. Then we invoked the Neumann boundary conditions. Of course, we also have to evaluate sigma square epsilon and omega epsilon, but that is something that we have done. To implement the Neumann boundary conditions, we have used these difference equations, and hence we have evaluated W0j plus 1 and W capital Nj plus 1 separately, so that in our tridiagonal system, the first and the last terms will be different. They will have different coefficients. All the other terms in between will have the usual LDU system. So then for an algorithm, from an algorithmic point of view, we have everything. We have the tridiagonal system. We have all the elements evaluated, either pre-evaluated if they are known functions, or they are evaluated recursively. So the G1, G2 functions are used in many places. They can be pre-evaluated, and the tridiagonal system is otherwise solved recursively using the usual order of n computation algorithms. So that's where we stand in terms of the PIDE. So is this okay so far?
Yes, sir.
All right, so we will finish this discussion. So as I said, I'm not going to discuss the PIDE in very much detail. I just took the simplest possible example, the put option, European put option, and how to do numerical evaluation of that when I have a jump process. So before I finish, I will just mention how we can use this technique for more complicated options like an American option. So we take one step forward. We have just done European put. So I just want to give you a sort of summarized view of how the American put can be handled. So this is due to Carr and Hitsa. So Hitsa as in the author of this book, and Carr is Peter Carr as of CGMY Carr. One of them is C is Carr. So Carr and Hitsa derived a forward PID for American puts. So again, it's a semi-martingale with Levi density Ky known. So now the forward PID that they have developed looks much more complicated because it's an American put. So I can actually exercise anytime I like. So again, it will be like a backward induction optimization. Remember, we did that earlier also for chapter 4 situations. So now our algorithm will give rise, if we do there is a lot of algebra involved. So you'll have this del P del T, the del 2 del x square, all the terms, then this integral for the adjustments. So this adjustment integral is similar to what we done before. And then I have this indicator and the additional adjustment terms, where if you recall, this is that synthetic dividend process. So if you remember in chapter 4, one of the approaches that we used for pricing American options was the use of synthetic dividends. So this is the same synthetic dividend approach used for American put again, but now the stock price has a more complicated nature. So because the stock price is now driven by a Levi density, it has jumps. So in principle, it is the same kind of work that was used in chapter 4 for American put using the synthetic dividend. But now the adjustments because of the jump process comes in. So I have this additional integral terms being inserted in the PDE as well as in the indicator. So I'm not going to ask you to go through the derivation because it is hard, it's not easy. But what I really want you to understand is how different things are related. So when you move from an European put with a standard Brownian motion model, we have the standard Black-Scholes. That's the easiest word. We have the analytical solution. From there, we go to path-dependent option pricing, American puts. Immediately, analytical solutions become unavailable. We come to numerical approximation. Numerical approximation we can do for American puts using some backward induction type of arguments, as in the Bermudan option or as in synthetic dividend approach. We make life one step more difficult. We introduce jumps in our Brownian motion model. So we work with the Levy density. When we work with the Levy density and we want to price American put, so European put we have just seen how to do. When we want to price American put, then we use that synthetic dividend approach along with the additional adjustments in the integral term. And that's what Carr and Hirsa derived. So this is the final equation that they have shown in the book. And the way it is handled is you again change to log stock price. So there is some change of notation. And with that change of notation, as in here, the PIDE looks like this. So it's the same PIDE, only now you have e to the power x in place of k, and here also. And the function capital P for the put is now written as small p because it has been redefined. So it is like the synthetic dividend approach as we used for the no jump case. Added to it the PIDE approach for the jump case, the two things together can give us a solution. The solution will finally look like this. And once you have a solution that look like this, then actually you know how to go forward and create a numerical algorithm for this one. Deriving this thing is hard, but once we have discussed how to do the European put in this chapter so far, this can also be done using a similar numerical technique. Okay, so we will stop here. Are there any questions right now? Because this is rather heavy empirical analysis, numerical analysis. You may need some time, but if there are some clarifications, then we will take that. Also, now that we are at the end of chapter 5, well, not at the end, but whatever I wanted to cover from chapter 5, these are the relevant problems from chapter 5. You can see on the screen now. Can you see it?
Yes, sir.
Yeah, so problems 1, 2, and 3, and case studies 1 and 2. That's what I want you to do from chapter 5. Right, so that brings us to the end of chapter 5. Next week, you have your midterm exam starting. So Best of luck, but stay safe, because I know that everybody has to come to the campus for the exam and situations are not as happy as they should have been. So take care, prepare, and we meet on 17th at my midterm exam at 11 o'clock. And before that, next week I am out. I will not be available for discussions. I am back on 14th. So 15th onwards, I will be available for discussions. Just to repeat, the midterm exam will be from chapter 1, 2, and 3, the first 3 chapters, and it's a 90 minutes exam, 1.5 hours exam.